By the way, okay, great. So today we start the lecture series and center lecture series, and the speaker is Fabian Haiden from Center of Quantum Mathematics in Odense, Denmark. The title of his lecture course is Quadratic Differentials, Stability Conditions, and Donaldson-Thomas Invariants. Fabian, please.
Okay, thanks, Jan. Yeah, it's an honor to give this lecture series at the M seminar. And since I'm given more time, I aim to tell a kind of complete story about, we'll present some of the work I did with Kontsevich and Kontsevich, and some more recent work, and some other ideas, which I've not written down all of them yet. But the main theme will be about this relation between quadratic differentials and stability conditions. And there's a couple of different approaches, so different groups of authors who worked on that. And I hope I can sort of give a bit of a unified picture that can in some sense explain or encompass, at least to some degree, all of these things. So what we'll do in lecture one is first talk a little bit about affine quadratic bundles, which I view as kind of a motivation for quadratic differentials in this lecture, and they'll play a more important role in the second lecture. But for lecture one, the purpose is talking about these is just kind of motivate why I'm thinking about quadratic differentials. And then quadratic differentials also have a nice interpretation in terms of flat surfaces. And so this doesn't yet involve any categories, so that starts in part 3, where I talk a little bit about this definition of a stability condition, Bridgeland, and then some modifications by Kontsevich-Soibelman, sort of remind you of that definition. And then I'll talk about the stability conditions on Fukaya categories, so which correspond to quadratic differentials, how that works. And yeah, if at any point you have any questions, please feel free to interrupt me. Yeah, so first I want to talk a little bit about these affine quadrics. So just a standard affine quadric over C, this kind of algebra geometric version of the circle, or the sphere rather. And yeah, you can do simple exercise. I promise this is the only exercise in this first lecture. This quadric is symplectomorphic to T star Sn minus 1. I mean, there's an obvious sphere sitting inside here, but the entire space actually symplectically is just its cotangent bundle. And now I want to consider a family of these fibered over a Riemann surface, so that the total space is a non-compact Calabi-Yau in the following sense. So I'll just really care about the complex structure, and that I have a holomorphic volume form. That just means an over-vanishing middle degree from the real analytic perspective form, top degree from complex analytic perspective. This is a picture where the fibers are where the case d equals 2, I guess. Yeah, and for now, just ignore that there will be no special fibers, just they'll come in a bit later. But now assume just every fiber looks like this. So if you have one of these things, then, well, locally what we can do is, so we have these fibers, remember, they're topologically just spheres, and we can integrate the holomorphic volume form along these spheres and get kind of general principle of integration along fibers. We get a one form on the base, but kind of little subtlety here depends really on the orientation also, right? We need to choose some. Locally, we can do that. We can orient all the spheres in some coherent manner, sitting inside these fibers. But globally, really what we get is, if we want to get rid of the sign ambiguity, we can square this one form And then we get what's called a quadratic differential, which by definition, it's a section of the square of the holomorphic cotangent bundle. So view the holomorphic cotangent bundle as a holomorphic line bundle, then take its square, and then its sections are quadratic differentials.
Fabian, what is
yeah.
a fine quadric bundle which you use as if you defined it? Let P x to C is a fine quadric bundle. So
yeah, as I kind of this situation.
But this situation is kind of depends on the coordinates, on the choice of coordinates. Probably you want something coordinate free. Yeah. So.
Well, I mean, I just want that every fiber is, isomorphic to this Q, or it locally trivializes with fibers looking like this. And this doesn't have any deformation that I care about. So.
No, your X is a Calabi-Yau, all right? So
X is
then,
open Calabi-Yau.
Yeah, great. But it's anyway, it's a real manifold. It's symplectic, all right? So when you say that something is isomorphic to the standard model, do you mean symplectically isomorphic, locally?
Yeah, actually, I don't care about the symplectic structure at all.
All right, just isomorphic.
Yeah, just the complex structure, and yeah. I mean, I said here symplectomorphic, but that's not actually important at this point.
Okay.
Here, it's important that it's just homotopy equivalent to the sphere. Yeah. Okay, so globally you get a quadratic differential, right? And if you write it, it looks like some holomorphic or meromorphic function times dz squared. There's a joke, kind of a tensor is something that transforms like a tensor. Quadratic differential is something that transforms like dz squared. Okay, so but now we also want to allow to have singular fibers. And let's just look at the sort of model situation where we have more singularity. So X is now just affine space, the standard holomorphic volume form. My projection is this quadratic function. So the more singularity, and we have so the general fiber of this is affine quadric, but the singular fiber has this ordinary double point. And if you look at the monodromy on cohomology, n minus first or homology of the fiber as you go around that singularity, then if the Calabi-Yau has odd dimension, there will be some change of orientation of this sphere as you go around the singularity. And if you compute phi, yeah, maybe there's some conceptual way to see how you get this exponent here. So as I said, right, if you can now integrate fiber-wise, which is what's written here, and then you take the square to remove sign ambiguity, you get a quadratic differential on the base curve. So here it's just c, and if you compute it in this case, it's just some constant times c to the n minus 2 dz squared. And what I care about is kind of this exponent here, which means that, depending on the dimension of this total space, I'll get a different kind of behavior of the quadratic differential near zero. So if it's 0-dimensional, I get simple pole. Then 2-dimensional, I sort of don't see it in the quadratic differential. It just extends kind of as a regular without zero pole. And then there's important dimension 3 is exactly the case when I get a simple zero of the quadratic differential. And so, sorry, here it should say 0, not pole. That's a typo. Yeah, it's by 4 and 5. So as I increase dimension, I get zeros of higher and higher order. Sorry, this should be a 0, not pole. Okay, so just example of this, which generalizes a bit this more singularity, but just still polynomial. So here X is this hypersurface, and C in affine n+1 space. And one way to write down the holomorphic volume form on this is to take Poincare residue of this. Well, you start with the standard holomorphic volume form on Cn+1, but then you divide so that this thing has a simple pole along this hypersurface. And you can take the Poincare residue, and that will be an N form on this hypersurface. And P is just the projection to the first coordinate. That kind of generalizes the situation where, P was quadratic before. And now to compute this phi, it's essentially the same polynomial here appears, but with some power depending on the dimension. So if N is 3-dimensional, then you get here this polynomial again. But right, if N is bigger, then you should get some higher multiplicity zeros. So you get some power of this polynomial instead when you look at the quadratic differential. And this is some picture of the situation. So these red dots are where the zeros of my polynomial, and over these I have singular fibers. And now kind of want to explain why it's called the 8K example. So if you, in general, if you take a path now between two zeros of the polynomial, then this can be lifted to a sphere. So I guess now here maybe symplectic structure does become relevant because there's a way to do that so that this sphere is Lagrangian. And then these spheres form. So if you can take the polynomial has degree k+1, and you can take k paths here which lift to these spheres, and they're kind of intersect in an AK configuration. That's where this name comes from.
You can get any Dinkin diagram kind of more complicated.
Not not for quadric bundles, maybe, right? Maybe you need more complicated fibers to get more complicated Dinkin diagrams.
Mm.
Yeah, I'm not sure if all Dinkin diagrams are realizable just by quadric bundle. I mean, you could do something like do this instead of C, do it on annulus, and then get affine version of AK.
I don't remember. I mean, it's like there is this emulsification story in singularity theory, but the ADE certainly can be obtained. So this is a bit different, but I think it's kind of very much similar. Like you have
yeah, except maybe the fiber will be more complicated, right? Than just Okay, and now we'll forget sort of about quadric bundles for now, for the rest of this lecture. They'll come back in the next lecture, but now there's a different point of view on quadratic differentials. So there was kind of a complex analytic. You view them as you have a Riemann surface and you have some section of the square of the holomorphic cotangent bundle. Yeah, one really kind of very neat thing is that you can also view them a kind of metric interpretation point of view. So the way this works is if you have a meromorphic quadratic differential and you look at the regular point, so away from the zeros and poles, take its absolute value, that is just going to be a flat metric. So it's a Riemannian metric, locally just flat, so isometric to the plane. And the charts, isometric charts are just given by integrating the square root of phi. And also you have, I mean, this is not really that much information, but you also have a foliation that comes from the quadratic differential, where you look at the vectors on which this is non-negative. It's real and non-negative, but it's some section of a square, so it's kind of like a quadratic form. And this foliation will be kind of parallel with respect to this metric. So if you, in a sense, if you know the foliation at one point, then you can just parallel transport it. You know it at all other points. So the only thing kind of that you, from the metric, that the metric doesn't know about this foliation is some kind of overall angle. But once that's fixed for every component, then that determines the foliation as well. Yeah, so that's what happens at generic points, and then near the zeros and simple poles, you find that the metric has a conical point. So it kind of looks like you glued several half planes together. So that, I mean, whatever what a cone looks like, you get some point where instead of 2 pi directions, you get some other angle of directions. And so here we see that, yeah, it's kind of related to this table I had before with the Calabi-Yau dimension. Namely, the multiple of pi here matches the Calabi-Yau dimension of this total space of the quadric bundle. Yeah, so if you have a simple bowl, then you just get cone angle, total angle pi. So it really looks more like a cone that you can embed in. If you think of a cone as sort of, it's being convex, not having less than 2 pi angle, it's more familiar. You can embed in R3. And then if you have simple zero, you get sort of excess, you get kind of negative curvature in some sense, that you have more angle than you'd expect the 2 pi. And then the angle, total angle of the cone increases as you get higher and higher order zeros. And then this is just a picture of what the foliation looks like. So you can think of that, you know, there's some number of half planes which you're gluing together, like these 3 half planes which have their standard horizontal foliation and which you're gluing together. Here's just 1 half plane glued to itself. Yeah, so what here the question is, what happens if you have a higher order pole and there the metric is already complete, right? So you don't sort of need to add this additional point, which was the 0 or pole before. That's sort of infinite distance from the other points. And also there's infinite area, then it's kind of clear that it's infinite distance, probably also infinite area. So kind of different behavior. And that leads to a certain dichotomy. There's kind of two classes of these meromorphic quadratic differentials. So the first case, if there's no higher order pole, then according to this table, there will be, I mean, the whole metric space is the whole surface. So you have finite total area. And if you, from a dynamical point of view, if you look at generic geodesics, or imagine sitting on this flat surface and kind of shooting a ray of light some direction, then it will wind around in very complicated ways, infinitely on the surface, and can come arbitrarily close to every point. Whereas if you do have higher order poles, well, then you immediately get infinite total area. And if you now shoot a geodesic in some generic direction, it's going to converge to one of the higher order poles.
Is it a relative of the fact that there is a Stokes phenomenon and you have exponential decay of the solutions?
Well, also if you have a double, right? If you have double pole, that's not really Stokes phenomenon. Because it's a quadratic differential, so it's like simple
square.
Pole.
For quadratic
right,
differential, sorry. Quadratic differential, it's a square, yeah. So then what's the reason for convergence for order 2? Say.
Well, for order 2, it looks like just you have an infinite, semi-infinite cylinder which is stuck to your surface.
Okay.
And a generic geodesic is just going to get kind of trapped in the cylinder and then travel along towards infinity. So you can sort of see that there's a region around the higher order pole that will trap any geodesic which enters it.
It's much simpler. It's like divergence of 1 over r square or something. Okay. Okay.
Yeah, so it's not really related to Stokes phenomenon. I mean, Stokes phenomenon will mean there's kind of some preferred directions at which it approaches maybe that corresponds to that. So if you have more than order 2, like a triple pole or something, then there will be certain directions at which geodesics will want to approach it. Yeah, so one more aspect about this flat geometry. What people study is, well, these generic trajectories, but you can also look at finite-length trajectories. So meaning smooth, so you'd only look at geodesics which are in the differential topological sense, not broken lines which have some kinks in them. So the smooth geodesics, there are just 2 types. Either they can end in both directions at a conical point. And this is called the Saturn Connection. And these are always rigid, so they appear discretely. And the other case is that you get a periodic trajectory. Like imagine you have a cylinder, then you can just take the loop around that cylinder. It will be a periodic geodesic, and you can see, but that just I can sort of move that parallel transport that geodesic loop, and I'll get a family, a one-parameter family of these geodesic loops, which together foliate some cylinder inside my flat surface.
So conical means it's pole of order 1?
Either pole of order 1 or 0 of any order. Yeah. So something which approaches in a simple pole or higher order, or 0 of any order. Yeah, and it can also be the same, so it could return to the same.
So if you have
a pole that's not possible.
If you have higher order pole, so as you say, generic geodesic, it has one endpoint there, and the other one cannot be the other higher order pole or not.
Yeah, so if you approach a higher order pole, then it's not finite length. So these are kind of
you're interested. Okay, sorry.
Yeah, I'm only now. If you're only interested in the finite length ones, then you don't approach any pole because that would be sort of infinite distance. Yeah, so this is only stuff that goes to the simple poles or to the zeros. Okay, and then actually, sort of, if you start, there's a kind of subfield of dynamical systems or ergodic theory, where you study these flat surfaces, and one of the questions you're interested in is counting. Since this is kind of rigid, and this is, well, these appear one-parameter families, but if you bound the total length, there will only be finitely many saddle connections and families of geodesic loops. So it makes sense to count them. And sort of one of the central problems in this subject, study flat surfaces, is to kind of determine these asymptotics. It counts some asymptotic formula or exact formula. And actually connecting it to stability condition will give some new insight about this problem. Yeah, so now kind of return about, kind of leave the flat geometry a bit behind and talk about the modulized space, where again I'm varying both the complex structure on the Riemann surface and the holomorphic or meromorphic quadratic differential. But what's fixed is the type of the zeros and poles. So, for example, if I have a double zero, it's not allowed to split into two simple zeros or things like that. So poles and zeros cannot collide and split and so on. So that from the flat geometry point of view, right, it means you always have the same types of conical points. And that sort of discrete data is being fixed, but the continuous data is allowed to vary. And from the flat geometry point of view, that means some kind of angles and lengths you can measure between conical points, that these will now vary smoothly. And yeah, important fact here, it's actually easy to understand kind of locally that it's locally modeled on this cohomology, which, so this complex vector space, which is cohomology of the curve C, where you remove the higher order poles, and it's relative to the zeros and simple poles. And
I'm a bit confused. So is it, I mean, if I fix a complex structure of C fixed, vary just phi, is it the same as the moduli of rank 2 Higgs bundles on C?
Yeah, so the base of the Hitchin system, you don't vary the complex structure usually.
Yeah, but then you can.
But here now I want to consider some moduli space where which also varies the complex structure.
Yeah, okay, but well, some people like to vary the complex structure for Higgs bundles too, so we have kind of more flexibility, more general.
Okay, yeah, that's possible. I don't know.
Yep, okay, but it's the same, yeah.
Yeah, I mean, here it actually becomes kind of easier once you include sort of both things, because then it's just described as flat surfaces, which is now yeah, so right, it might be kind of difficult to know on a particular Riemann surface if it has a holomorphic or meromorphic quadratic differential of a certain type with certain prescribed zeros and poles. But if you're kind of also allowed to vary the complex structure, then that sort of becomes a more, yeah, somehow it becomes simpler to describe this modulized space. Yeah, so it's locally modeled in this on this cohomology, just a complex vector space. Yeah, here this is, so it's the space surface minus the higher order poles, and it's relative to these conical points, the zeros and simple poles. And its coefficients in kind of a twisted version of C where you twist by the square roots. So you can think of it as the flat line bundle, which has monodromy around the zeros, or at least the odd multiplicity zeros and the simple poles.
Why is the strange choice of coefficients?
I mean, that's because if you have now a quadratic differential, right, then it will actually define a somehow, yeah, this is naturally what you can assign to a quadratic differential. If you compute some period of this quadratic differential, so you want to integrate it along some curve, then you need to choose a square root to get a one form. So the periods are kind of only defined for this twisted coefficients.
So if I already kind of started with a holomorphic, meromorphic one form, then I will look just for homology with coefficients in C. Yeah, because the same question can be same questions can be asked for meromorphic one form, so your differential will be just square. I mean,
right.
People, yeah, okay.
Yeah, so if I were not to care about quadratic differential, but just abelian differentials, one forms, then I wouldn't need this. Yeah, and there's also, this is just kind of to mention, because later we'll see that stability conditions have a similar property that you can act on this by GL plus 2R, which this action sort of mixes really, this changes both the complex structure and the quadratic differential. So yeah, so if you just consider, if you fix the complex structure, you wouldn't have this action. So this acts by, if you just think of the quadratic differential kind of as a complex, or if you think of as an abelian differential as a complex valued one form, then you can take that complex value and act by GL plus 2R and get something that's complex for a different complex structure. Yeah, not sure if that makes sense, but this action definitely.
Yeah, what's the action? I mean, there are, I have in mind a couple of ways to define it, but can you?
Yeah, so I mean, if you have a let's say abelian differential, then it's something which takes values in C, and you can just sort of concatenate that map which takes values in C. So at every point you get a functional map to C, and you compose it with this matrix and get a different map to C, which will be complex for a different complex structure on the tangent space. So it's composing, it's kind of post-composing with this. But another point of view, in terms of the flat geometry, if you think of your flat surfaces obtained from some polygon where you have identified edges, like imagine the torus, for example, comes from some parallelogram with identified edges, then you can just act on that polygon using this transformation of the plane. So it's kind of clearer what this is from the metric point of view.
Mm-hmm.
Did that answer your question?
Yeah, it does. Yeah. And later okay. You will explain how it comes from the action on the central charge and so on. So.
Yeah, so the point will be that on stability conditions, you also have this action. And that was kind of one of the first hints that the two should be really identified. Yeah, and actually I mean, this is not super important, but kind of more of a remark that if you look at the diagonal part in here, given by these sorts of matrices, then it corresponds to the action of geodesic flow on Teichmüller spaces. So Teichmüller space cotangent bundle to modular space of Riemann surfaces. And actually, a cotangent vector to a Riemann surface is just a quadratic differential. So this modulized space is also kind of sits inside cotangent bundle to Teichmüller space. And so if you look at the action of geodesic flow, it preserves particular component where you fixed multiplicities of zeros and poles. And yeah, that's part of this action. Okay, so now, yeah, something I mentioned that there's some kind of moduli spaces which look a lot similar. And so they look similar in the following way, that they're kind of complex analytic orbifolds. They have a wall and chamber structure. And they have this action of G plus to R, or in the case of stability conditions, actually universal cover of this. And so the expectation, I think that's, well, definitely, I think Kontsevich and Paul Seidel sort of noticed this, and maybe some other people as well, that there's probably some statement that if you take the Fukaya category of the surface, and you look at its space of stability conditions, so I'll define these in a moment, then this looks like it's the space of quadratic differentials, flat surfaces. And then in some joint work with my advisors, sort of made this statement precise. And so it's a sort of question about exactly which maybe Fukaya categories you want and so on. And I'll say what the results of that are. But this is now just, I'm motivating, we'll talk about stability conditions next. And I just want to know how do you get from flat surfaces? Why am I now suddenly talking about stability conditions? So this definition of Bridgeland, and then changed with some small modifications, which have now become standard to also include this group gamma and the so-called support property. So we're fixing a triangulated category, and we're fixing something which sort of plays the role of a Chern character. So just that this K0 of my general, typically this is infinitely generated abelian group. And we just want some map to maybe often quotient, but doesn't need to be, to some finitely generated abelian group, which is also fixed. So sometimes this is numerical K theory, for example. And then a stability condition, it's defined by two pieces of data. So first you have an additive map from this group gamma to the complex numbers. So in particular, right, since we have this map from K0, that gives you a map from K0 to the complex numbers. So for each K theory class, has some place inside the complex plane. So that's sort of easy to specify usually. The more complicated piece of data is for each real number, I should also specify the semi-stable objects of that phase. Yeah, and actually this is usually kind of trivial except for a countable set of phases. So this is not really a data for uncountably many real numbers, but just usually for countably many. And it's kind of zero subcategory for most real numbers. And so, yeah, it should be a full additive subcategory. So it's essentially some collection of objects, and it's closed under taking the direct sum. Yeah, and now this has to satisfy a bunch of axioms, and they will be sort of familiar if you're used to semi-stable vector bundles on Riemann surfaces. So the first is that if I change the phase, if I shift the object, then I get a semi-stable object with phase shifted by pi. If I, yeah, there's two conventions, maybe sometimes shifting by pi or by 1. Yeah, here I wrote the form where it's shift by pi, so normalization. Yeah, then the second, there should be no morphisms, just a zero morphism if you from a semi-stable object of bigger phase to a semi-stable object of smaller phase. And then the third one is whenever you have a semi-stable object, then this phase should be a choice of argument of this central charge, right? So E, and this is kind of shorthand notation for this object E has some K-theory class and apply CL, and then take its central charge. So this is some complex number, and phi should be a choice of its argument. I mean, and also it should be a non-zero complex number whenever E is semi-stable for that to make sense. Yeah, and then here axioms continue, but this is there's only these two more. There's not another page of axioms. It's a little bit of a long-winded definition, but it fits on 2 slides at least. And this is kind of a very significant one, so one that's kind of hard to check. I mean, these are kind of trivial to get this periodicity. Yeah, maybe these, I mean, depending on your approach, they may or may not be hard to check. But for our result, this one was the hardest to check because it says something really about every object of the triangulated category. It's not just a statement about the semi-stable objects. And it says that if you have any object, you can get it as an extension of semi-stable objects in some canonical way in order of decreasing phase. So what you can actually show is whenever you have 2 towers like this of decreasing phase, they need to be the same. So there's an automatic uniqueness here. But you just need to require existence of these filtrations. Yeah, and then the last one called the support property, which was introduced by Kontsevich-Soibelman. It's now pretty standard to also include this. Yeah, Bridgeland's original definition had something kind of similar, where also this was somehow you had the central charge defined just in K0 instead of this gamma. But anyway, yeah, what does the support property say? It says that there's a norm on this lattice gamma, so that for any semi-stable object, so if you have to take a class, which is now a class of some semi-stable object, then its norm has some upper bound or given by the central charge. Right, so I mean, the other way would be it just follows from continuity, but to have this, that's not going to be true for all gamma usually, but you require it for semi-stable, those which support a semi-stable object to satisfy this inequality. So it says something about all the lattice points in this lattice which support a semi-stable object. It can't be too big. There's some constraint on how it maps to the complex numbers. Okay, so that's this definition. So probably good to have an example, and a canonical example. If you take bounded derived category of coherent sheaves on the smooth projective curve, and for this gamma, we'll just take basically rank and degree, which take numerical K theory. Then that's isomorphic to the C squared. The central charge is given by, yeah, basically you combine degree and rank, so that the phase of that central charge will correspond to essentially the slope of the object E. Right. So, I mean, what people did before Bridgeland stability was just look at degree of a rank, and that was called the slope, and that's now encoded in this in terms of the angle. And so, what are the semi-stable objects? They're just semi-stable vector bundles of the correct slope. So semi-stable just means there's no proper subbundle of bigger phase. So that's true that's a correct definition for vector bundles on Riemann surface. In higher dimensions, you'd want there to also be no coherent subsheaves. Yeah, and C1, so then you sort of have to combine also the torsion sheaves, kind of put them in the category. Basically, any indecomposable here will be either a vector bundle or a torsion sheaf, and you need to deal with them separately. So things of phase 1. Yeah, I think here I kind of switched connection. So maybe this one should be pi if I'm consistent with this. My previous convention here. Sorry about that. Yeah, so this should really be pi here and pi here instead of 1. And for general phase, just by this periodicity requirement in the axioms, there will be a shift of these. Yeah, so and that will be an example of a stability condition. Yeah, interestingly, this doesn't generalize to higher dimensions, so that it's much harder to construct stability condition if you increase the dimension of X. And for 2, it's still possible, and for 3 also in some cases, but then as the dimension of X gets higher, this gets kind of very complicated. But I mean, that's sort of a B-side example, and we'll kind of focus more on the A side now. So we'll look at Fukaya categories. But before we do that, yeah, a general fact about stability conditions that they have some moduli space. So you look at the set of all stability conditions on a given triangulated category. So here, this gamma and CL are also fixed. And then, so what Bridgeland had a remarkable result that you can put some natural topology on this. And what then becomes true is that there's an obvious map from stability conditions to Hom of gamma C, which just forgets the collection of semi-stable objects and just remembers the central charge. And he showed that this is a local homeomorphism. So intuitively, it means if you to deform a stability condition kind of locally is just the same as deforming the central charge. So I mean, what you have to do to prove this theorem is kind of if you vary the central charge a little bit, you need to compute some new collection of semi-stable objects, which again satisfy all these axioms. And as a consequence, you can just use these maps as kind of local charts for a complex analytic structure. So this is a complex vector space. When you have a local homeomorphism, so you automatically get a complex analytic structure of dimension the rank of gamma on this space of stability conditions. Okay, so it's kind of really surprising in a way. You started just with some triangulated category, which could be defined over a finite field, for example, and then you get some complex analytic manifold out of it. So it's a bit weird from a mathematical point of view, definitely. But I mean, sort of intriguing, and there's been a lot of work on trying to understand what is this complex analytic manifold in for particular choices of C. Yeah, and that this turned out to be a pretty difficult problem. And one of the upshots of this things I'll talk about in this lecture series is that for some C, we can understand all of this in terms of quadratic differentials. Okay, so now a few words about the choice of category, where we'll look at stability conditions on these wrapped Fukaya categories of surfaces. And so the setup here is you have a compact oriented surface, some punctures, and so to get a kind of a C grading on the category, you need a foliation or section of the projectivized tangent bundle of S. So just a line in the tangent space at each point. And so it doesn't really, we only really care about this up to homotopy of sections. Yeah, and I mean, you can also put the symplectic form or exact or primitive of symplectic form or something, but that doesn't really play much of a role here. I mean, you can also, there's ways of defining this without choosing any symplectic structure. I mean, anyways, in this dimension, there's not really much symplectic topology. Yeah, so if you have all of this data, then, and also choose some base field, just completely arbitrary, then there is something called the wrapped Fukaya category of the complement of these mark points with respect to this grading structure. This is an infinity category over the base field. Yeah, and I don't want to go into all the details of that definition, but I guess the important thing to know is just that objects in here come from curves. So Lagrangians in this dimension are just curves. And they need to, if they have endpoints, so they could be closed curves, or if they have endpoints, then these endpoints need to find M, or you can think of them as approaching infinity if you remove M, approaching the punctures. And they also come with some grading, which is some kind of lift to, well, you can think of it as some way of a homotopy between this line field nu and the tangent spaces of my curve C. And then also they come with a flat bundle of k vector spaces. I mean, that could be just a trivial one-dimensional bundle, but yeah, it's also useful to consider more generally if you do some higher dimensional, but still finite dimensional flat bundle over I. And yeah, just one result about these categories, which is important for constructing these stability conditions, to prove in this paper with Maxime and Ludmil, that there's a kind of tame representation type result. So if you look at these sorts of objects, so it's a curve, K has this grading, which is not particularly important. It's just some discrete choice, and you have these flat bundles over it. Then they form some infinity category, and the statement is that of this theorem is that this infinity category is already triangulated. So it has shifts and direct sums and cones. I mean, it's kind of clear it has shifts because you change the grading. It's clear it has direct sums. You take basically disjoint union of curves. But the tricky part is it also has cones. If a cone is kind of a formal object, and this says that this formal cone is actually represented by some curve, which I mean, roughly how you can think of it is that I take these two curves and then I smooth some of the intersection points to get the new curve, which represents the cone. But yeah, it's a bit more complicated. But if you try to prove an exact statement, but I mean, the importance is that we can really understand all right, because the Bridgeland stability conditions should be something that's defined on a triangulated category. And here we can understand all objects of that triangulated category, just kind of very geometrically in terms of curves with flat bundles. Okay, any questions at this point? Okay, now continue. I think we'll get yeah, we'll get to the main point now. Yeah, so the setup now, right? This was kind of in general for any just topological surface with this grading structure, this line field. Now, if we have a compact Riemann surface and a quadratic differential, narrow morphic quadratic differential, in this case, we'll take M to be some set containing the zeros and poles, which means it's basically the set of zeros and poles, but plus we can also have some additional marked points around which we wrap. And then you consider the foliation you put is just a horizontal foliation of the quadratic differential. That's how that comes in. And also you need to pass to a subcategory which avoids all the higher order poles. The problem is if you have some curve and it approaches a higher order pole, that's a perfectly fine object in this wrapped Fukaya category. But right, if you try to define a central charge, we would want to integrate along this curve, we would get some infinite answers. So if we want our objects to have some finite central charges, then we need to restrict to objects which don't approach the higher order poles. So that will be just some full subcategory in this wrapped Fukaya category. Yeah, if you don't have any higher order poles, then no, it's just the same category. Don't need to do this step. Yeah, so then this kind of first part of our main result is to construct a stability condition on this subcategory here, where the central charge is given by just integrating square root of this quadratic differential. Yeah, and the kind of choice of square root is encoded in grading structure in some sense and also orientation. I mean, there's some way to make sense of, there's no sign ambiguity here that everything sort of fits together to eliminate all sign ambiguities. So what are the semi-stable objects? So they are, I mean, what in general in higher dimensions you'd call a special Lagrangian, and then in this dimension are just geodesics, straight lines. Yeah, Jan, you have a question?
No, you cannot notify.
Okay, apparently not. Yeah, so the yeah, so semi-stable objects are those curves which are smooth geodesics. So these saddle connections and closed loops, and possibly unions of several semi-stable objects which are decomposable. So indecomposable semi-stable objects are just saddle connections and closed loops, and then all semi-stable objects are just direct sums of these of the same phase. Okay, yeah. So the theorem is that once you define a stability condition like that, then it really is a stability condition. It satisfies all these 5 axioms I listed in the beginning, and they're basically all pretty trivial. Also, the support property is not very difficult. But the most difficult thing is this Haiden-Simon property. So remember that told you that every object in your category was some extension of semi-stable ones in decreasing order of phase. And now this is where this geometricity property comes in, that we can understand all objects in a geometric way. So here's a kind of sketch how to prove this existence of Haiden-Simon filtration. So you start with arbitrary indecomposable object in this category. It's represented either by a closed curve or with possibly some higher rank flat bundle on it, or a curve between 2 of the conical points. And then for that curve, you have some unique geodesic representative, which will be kind of not a smooth geodesic, but in general, it's some sequence of smooth geodesics, some it's just broken at certain points, at the conical points. So it kind of goes from one conical point to another, and then it can change angle, and then it can go to another conical point and change angle again, and so on.
Can we think so? Sorry, I am kind of the internet, so I missed part of your talk. Yeah, but anyway, can this collection of geodesics can be thought as a degeneration, like of the curve, which is Lagrangian, and so there is a very general idea that you can degenerate smooth Lagrangian into kind of extension of special Lagrangians, like which correspond to Haiden-Simon presentations for this smooth Lagrangian. Is it the same kind?
Yeah, definitely. So I think, that's something that I was planning to talk about more about the next lecture. Some higher dimensional conjectures which generalize this to higher dimensions. And there, arbitrary curve means Lagrangian, and then geodesic means special Lagrangian. And this geodesic representative means you can deform Lagrangian to a special Lagrangian. But which in higher dimensions is a very difficult question, but just in this dimension.
Yeah, the only thing which confuses me is the part 1. It says that any indecomposable is just a closed curve. It's something which is not part of the higher. Will you have an angle of 1 in higher dimensions? Because it's
in higher, not exactly. Yeah, so this is reflecting the tame representation type of. So what you have in higher dimensions, you also have every object in the Fukaya category is some Lagrangian, but it comes with this bounding cochain, right? This additional algebraic data that is concentrated at.
Compressibility is a difficult property, and I understand that in homological dimension 1, you can say something like for quiver representations or for curves, at least of lower genus, but in higher dimensions, it's a wild problem description of indecomposable.
Yeah, definitely, I agree. And you can also see that what this is saying is that if you started with a curve which had some bounding cochain, so it has some kind of coefficients at the intersection points, which was a formal deformation of that object, then you can get rid of this bounding cochain by changing the underlying curve by doing some smoothing. but that's not going to be possible in higher dimensions, I expect.
Okay.
Yeah. So somehow we can just reduce to something purely geometric in this dimension, but yeah, probably in higher dimensions, you really need to take seriously this bounding cochain, this additional class in degree 1 element that is finding more quantum equation. Yeah, but definitely this approach sort of doesn't generalize to higher dimensions sort of as is. It's yeah, particular to this dimension. Yeah, so once you have this, you have a geodesic representative, so you can imagine some concatenation of smooth geodesics, and these pieces will then correspond to the semi-stable factors in Hada's infiltration. I mean, more or less, might be direct sum of several pieces will be one semi-stable piece in here. And then sort of putting these individual straight lines together corresponds to forming this iterated cone in the Hada-Namas infiltration. So yeah, so to prove existence, you need to give these semi-stable objects that will correspond to these geodesics. And to show that their extension, their repeated cone, gives you the original object that some statement about concatenating curves corresponds to taking cones. Okay, so that's kind of outline of how that. And then, yeah, so now this is sort of a statement about just one stability condition. So it tells you, start with this quadratic differential, you get a stability condition, but then we actually prove a bit more about computing an entire component of the space of stability condition. So now we want to look at the modulized spaces. So again, we fix an oriented surface, some punctures, this grading structure, and then there will be some modulized space of quadratic differentials which are kind of compatible with this. So, well, remember, we also vary a complex structure, and it's a quadratic differential which has its zeros and poles in M. And you want a homotopy also between this given grading foliation and the horizontal foliation of Y. So that having this homotopy tells you in particular that the zeros and poles of phi will have kind of the correct, they have some fixed order, which is the winding of this foliation around the points in M. But yeah, we don't just require existence of a homotopy, but this is part of the data. So it's more like Teichmüller space than modulized space. That it's kind of additional markings like going to a universal cover of the modulized space. Yeah, and then what we prove is there's, I mean, this kind of previous result gives us a natural map from this modulized space of flat surfaces to the space of stability conditions on this Fukaya category. And yeah, basically, it's all we almost know that this is an isomorphism of moduli spaces, except that there could be some additional components of this space of stability conditions which are not in the image of this map. So one way to say is it's biholomorphic onto its image. The image is a union of connected components, so it's not like you're just getting a part of a component from quadratic differentials. But what we cannot rule out is that there's not some kind of exotic components which don't correspond to quadratic differentials. Yeah, actually, though, this is a student of Schende, Alex Takeda, proved that this is in fact an isomorphism in at least in the cases where this is the so-called partially wrapped Fukaya category. But as far as I know, yeah, if it's in exactly this case where it's the wrapped category, this is still kind of an open question. Although I expect it's just there's not any of these exotic components. I do expect it to be just an isomorphism, but not sure how to prove that. Yeah, and then yeah, as I mentioned, these partially wrapped categories, there's a bit of an extension which I haven't talked about so far. I'll just dedicate one slide to. Instead of looking at the wrapped Fukaya category, you can look at so-called partially wrapped Fukaya category. And these also depend on the same old package of data, but then also at some of the marked points, you also choose some number of tangent rays. And then your Lagrangians kind of need to enter in the direction of these tangent rays. And the quadratic differentials, which give stability conditions on these kinds of categories, are not meromorphic, but they have these, I mean, transcendental but not very complicated sort of exponential type singularities. So they look like x of c to the n, and then maybe times some meromorphic factor. And from point of view of flat geometry, it's kind of very natural generalization because it means allowing cone points which have infinite cone angle, as opposed to just cone angle being a multiple of pi. But you can think of it as kind of limiting case. The cone angle becomes bigger and bigger, and in the limit, I get an infinite cone point. Yeah, and simplest example here, if I take a disk, it's kind of corresponds to the case where I have P1 with marked point at infinity and n+1 directions at that point. And here, this partially wrapped Fukaya category is the bounded derived category of the path algebra of the AN quiver. And quadratic differentials, which correspond to stability conditions, are of this form: x of some polynomial of degree n+1 times dz squared. So this is actually was kind of in this whole project sort of reverse order, that first understanding this example and then all its generalizations. Okay. Yeah, but then now this is my last slide, and I just want to kind of explain how I continue this lecture series. So, I mean, this is a nice result. It tells you this correspondence of moduli spaces of quadratic differentials with stability conditions on wrapped Fukaya categories. But you'll notice that we kind of forgot about all this higher dimensional Calabi-Yau geometry, which I talked about in the beginning, which was, you can sort of see as the source of this quadratic differential if you want, if you're sort of interested in Calabi-Yaus more than maybe flat surfaces. And one way that's reflected is that this wrapped Fukaya category, it's one Calabi-Yau, right? It's really just kind of reflecting the geometry of the surface. It's not reflecting the geometry of this quadric bundle. And it's also smooth. So yeah, this Calabi-Yau is in the sense of smooth categories, but it's definitely not proper in general. And then if you go to the subcategory, it's kind of a bit of a bad category in the sense it's neither smooth nor proper. So it doesn't even make sense, or it's not obvious how to say it's Calabi-Yau. And we'd really want to replace this category by something which is a bit better behaved, which is more or less the Fukaya category of this quadric bundle. At least if it's dimension 3, then we expect that we get a proper 3 Calabi-Yau category, which is needed as a kind of input for this theory of counting semi-stable objects, what's called motivic Donaldson-Thomas invariants by Kontsevich-Soibelman, which will be, which will allow us to count semi-stable objects and relate these back to counts of saddle connections and closed geodesics, which I said was kind of one of the central questions in the subject of flat surfaces. But yeah, for all that, you definitely need a proper 3 Calabi-Yau category. And this wrap category is not it. So we'll continue next time to talk about how can we get back to this higher dimensional Calabi-Yau geometry. Okay, and I'll end here. Thank you very much.
Yeah, thank you. Are there any questions? We're a bit over the time, but nevertheless, are there any questions? If there will be questions, you'll be able to ask Fabian on Wednesday. So
everything was there.
Well, I do have some questions, but it's because rather because I was cut from the internet. It was terrible, so maybe it will happen again. But anyway, so the next lecture will be on Wednesday, so same time, which is 1:30 local time. Thank you, Fabian, and see you on Wednesday.
Yeah, see you Wednesday. Thank you.